What I do want to talk to you about, though, is rotational kinetic energy. And so I want you to picture some object that has a physical radius or dimension. Let's assume for now that the object is a solid object, so there are particles distributed from the center all the way out to the exterior. We're going to take this, and we're going to grab a hold of it, and we're going to spin it. Let's call it in the clockwise direction. We're going to spin that at an angular velocity omega. When we describe kinetic energy, right, we need a velocity of the object moving as it moves translationally, as in moving over a displacement covering a distance in its motion. That is typically how we describe motion. When we describe kinetic energy, it's in terms of linear motion, v, right? But if I had an object like this and I just spun it in place on an axis, we could still say that it has energy, right? Because it is moving. But in terms of the way we've described kinetic energy to this point, V would be 0. And so that is an inappropriate application of kinetic energy for a rotating object. Does that make sense? So in order to properly describe the kinetic energy of an object that is not moving translationally, but is instead rotating, we need to consider the fact that each individual particle has a velocity, right? And so those particles would be obviously everywhere within the medium. But what's key is that the velocity of each individual particle is the product of the radius it is away times the angular velocity. Because the angular velocity is a measurement of the rotation rate, and the rotation rate, like 2 times per second, is the rotational rate for all particles. But their individual linear speeds vary based on where they are. So a particle that's out here would be the radius of particle that is here. That would be the radius of particle that's over here. That would be the radius of particles that are on the exterior perimeter would be the actual radius of the device, and so on, right? And so the key thing there is that each individual component of the material is actually rotating with a slightly different linear velocity, right? And the bigger the object would be, the bigger those differences would be. That makes sense? All right, so when we describe rotational kinetic energy, KE rotational, capital R, we would say that it is essentially the sum of the kinetic energies of each individual mass, where we've actually added up all of the individual kinetic energies for each individual atom, right, for all intents and purposes. And so what we're going to do is we're going to expand this and change things a little bit to derive our relationship of kinetic energy rotational, KER. And so we're going to expand this into the formula for our standard kinetic energy, right, sum of 1/2 mv squared. But then we're going to take the fact that V for each individual particle is dependent on where it is, right, R times omega. And so this turns into the sum of 1/2 m times R squared times, omega squared. And I've written them as R times omega specifically here so that I can group this set of terms. But before we get to that, it's important to note something that I've said a couple times already, is that the omega is a constant value for all the particles, right? So in terms of a sum, omega is a constant. So is 1/2, right? And so I can pull those out in front of the sum term. So this is 1/2 omega squared times the quantity of the sum of mr squared, right? And this is possible because omega is constant for all particles. This is only true if the object is a solid, right? It's possible that omega would not be constant for all particles if you were looking at something like a gas or a liquid. And you've all seen this before because of that water bottle trick, right? Where you flip the water bottle and stands upright. When you spin the water bottle, it doesn't keep spinning because the water inside has a different rotational rate than the actual bottle does on the outside. Make sense? So this is only true for solids, but nevertheless, that's what we'll be working with. But the key here is that this term, the sum of m times r squared, is a term we've actually already looked at. That's the moment of inertia. So for a rotating object, that's I, right? Remember that I is the sum of all the particles based on their relative location. This is the inertia characteristic of the torque that they generate based on where they are. And so that means, right, that this statement, the kinetic energy of a rotating object, can be thought of as 1/2 I omega squared. And we've written it in this particular order so that it mirrors our linear kinetic energy formula, right, 1/2 mv squared. And we can talk about it in the same terms, right? Kinetic energy is dependent on mass and velocity. Kinetic energy of a rotating object is dependent on its mass factor, or its inertia factor, right? And its rotating velocity, omega. That makes sense? Okay, so the application of this is pretty straightforward, but it's important because it's something that the AP is definitely going to challenge you with, right? So the example that I'm thinking of is a sphere rolling down an incline. So if I draw an incline, looks like this, and I define this as a height h, and I put a sphere on here that has a defined radius of lowercase r. But I'm being specific in saying that this is a solid sphere, right? Then the question will be, how fast is it moving when it rolls off the bottom? In other words, v prime at the end of the incline is what? And this would be all on an incline that we can define on an angle as theta. And so typically, in problems that we've been working on so far, we've just done PEG to KE in order to solve the problem. Now that is only now appropriate for something where we can't consider the rotation of the object itself, right? And so now if we're rolling things like spheres, balls, cylinders, and rings down an incline, we have to take into account the fact that some of the energy doesn't go into translational motion, but instead goes into rotational motion, right? So the example of something that we've been doing currently that we can continue to think of being as an object are things like cars and carts, right? Because the overall mass of those systems are such the individual energy of the rotating tires is small enough that it can be neglected, right? So we just think of the car rolling down the hill, starting at potential energy and ending at kinetic energy and solving for V, right? This, on the other hand, when we do E equals E prime, we need to say that this goes from potential energy due to gravity at height h equal to kinetic energy prime of the translational motion plus the kinetic energy of the rotational motion. And so based on the formula that we just went through, this expands to be mass times gravity times height equal to 1/2 mv prime squared plus 1/2 I of a sphere times omega squared. Now the key there is that there's not enough like terms of these two terms along with the potential energy to do much work. And so what we want to do is we want to substitute information into this last term so that we have more common variables across the equation. And so that's all to say that provided to you somewhere is the moment of inertia for all those various shapes that we went through. And the moment of inertia of a sphere is 2/5 mr squared. And then don't forget, we just had the formula for linear velocity as r times omega, which means that omega can be thought of as v divided by r. So what I'm going to do is I'm going to take those two things and substitute them into the terms here and then collect like terms, right? And so this rewritten as mgh equal to 1/2 mv prime squared plus 1/2 times the quantity 2/5 mr squared times a new quantity, v squared over r squared. So I've substituted the moment of inertia formula in specifically for a sphere in this case. That will change depending on the object that's rolling down the hill. And then omega in terms of v and r. Now the reason why we did that is that introduces mass into this last term. And so mass is multiplied here, here, and here, which means that it drops out across the equation. Right, it cancels. And then secondly, the mr squared here and the fact that omega is inversely proportional to r squared now means that this r squared multiplied by the inverse of r squared cancels out that term also. So this cleans up a good bit, right? And so what we have is g times h equal to 1/2 v prime squared plus 1/2 times 2/5 times v prime squared. And then in this particular case, the convenient fractions actually cancel one another because this 2 cancels this 1/2 and leaves 1/5. And so then v prime is the linear velocity at the bottom of the hill and is actually common to both. And so g times h is equal to 1/2 plus 1/5 as a quantity times v prime squared. And so then to solve for v prime is to rearrange and get the square root of 10/7 GH. So then the real question, right, is if I'm looking at this up here, is this square root 10/7 GH faster or slower than what it would have been if we'd have just considered this as a point mass moving from up here to down there? Is it moving translationally slower than it would be as our previous calculations, or faster? It's hard to picture, right? And so if we go back and think about how we would have solved this when we were thinking about just cars rolling down a hill, we'd have gone from PEG to KE prime only, right? This is what we were doing when we did conservation of energy. And so this would be MGH equal to 1/2 MV prime squared. The m's cancel, and v prime is the square root of 2GH. Right? Is 2GH larger or smaller than 10/7 GH? It's bigger, right? So if we were to calculate this in the traditional fashion, we would get a speed that is actually higher than what a real dimensional object would be moving, right? And the reason is because some of the energy breaks off into rotation, right? And rotation is not translational movement forward. And since energy cannot be created or destroyed, the act of spinning is slowing the overall forward progression, right? Because it's drawing energy into making the system spin without necessarily making it move forward. Calculations like this, right, will be exactly like this, save for this equation, right? Depending on the shape of the object, this I term will change, right? But always there will be some energy that's given off as a rotational motion. So we'll always expect this speed to be less than a point mass or a car if we're doing the basic calculation, right? But that fraction, this fraction here, is dependent on the fractions that cancel in this term. And this fraction in the 2/5 is dependent on the shape. And so solid spheres, solid cylinders, hollow rings, and so forth all introduce new fractions, right? You don't have to memorize those formulas, but you do need to be aware that they are part of the component now that you have to consider, right? An AP question will be specific, and so if they are identifying an object that has a dimension with a distribution of particles, then they will clearly state a solid sphere on an incline, right? And then they will also probably prompt you by reminding you some of the I equations. But that's something to be on the lookout for. Does anybody have any questions?